Here I have a function in green, and I'm going to pick a point on the function, let's say right there, and I'm going to label its x value, well, just simply x. And that means its height, the height of that point, will just be f of x. Okay, and then I'm going to draw in the tangent line at that point. And the main focus of this video is going to be about finding the slope of that tangent line. Well, first let's remember what slope is. So slope is y2 minus y1, change in y, divided by a change in x. So x2 minus x1. And this is the slope of the line that runs between those 2 points. So that's important. To be able to use this formula for slope, we need 2 points. We need the point x1, x1, y1, and we also need the point x2, y2. The problem for us is this tangent line, we only know one point. We know this point of tangency, but we don't know any other point. We don't know this point, we don't know this point, we don't know this point, we don't know this point. We don't know any other point on the tangent line. So we're not going to be able to use this directly, because we need 2 points, but we only have one. But we're not going to give up. What we're going to do is pick another point on the function, because we can always find points on the function. And now we can draw a line between the point of tangency and this point up here, what I'll call the estimation point. So we have that line, we have 2 points on the line, so we can find the slope of that line. And just by the way, this line here is called a secant line. So we could find the slope of that line, and we'll say, hey, you know what? The slope of the pink line, the secant line, is approximately the slope of the tangent line. So it's an estimate. You know, it's not perfect, but they're kind of similar. And then we say, well, you know what? We want our estimate to be better. So we move our estimation point a little bit closer to the point of tangency. And hey, that line there, the slope of that line is a better estimate of the slope of the tangent line. So we say that worked pretty good. Let's move even closer. And now we have an even better estimate. So we say, hey, you know what? Why stop there? Why not move even closer and closer and get better and better estimates? So we're taking our estimation point and we're approaching the point of tangency. And that should start to sound like a limit to you. And that's exactly what's going to end up happening. But let's go back and start formalizing things. So that's the concept behind what's about to happen. But let's start formalizing it and labeling it. So we'll start with our original estimation point, and let's give it a label. So our original x value, we start at the origin and we move over by x. And then to get to this estimation point, we move over just a little bit more, what I'm going to call h. So we've moved over by x, and then plus that, we've moved over by h. So this x value here is simply x plus h. Now, why did I call it h? I don't know. That's what's commonly used. Okay, so x plus h, that means the height of that point is f of x plus h. Okay, and now there's a line that goes between the point of tangency and the estimation point, like we talked about, the secant line. And we want to find the slope of that line so that we can estimate the slope of the tangent line. Okay, so the slope of the secant line is going to be f of x plus h minus f of x. So I'm color coding this so you can see where it came from. It's just y2 minus y1 divided by x2, x minus h. Sorry about that, x plus h minus just x. So again, this is just x2 minus x1. And this is the slope of this secant line here, which we wanted to find because we said it's approximately the slope of the tangent line. Now notice that there's an x and a negative x. Well, those are just going to cancel. And so we're just going to be left with an h in the denominator. But don't let that confuse you. We're still just talking about slope. It just happens that those x's cancel. Okay, so this is approximately the slope of the tangent. And then what did we say we wanted to do? We wanted to move closer to the point of tangency. So we're going to do that closer and closer and closer and closer and closer and closer. As we do that, what happens to h? Well, h gets smaller and smaller and smaller and smaller and smaller and smaller. So as h gets smaller and smaller, our estimation point approaches the point of tangency. So what we want to happen is we want h to be as small as possible, infinitely small. So we take a limit. We take a limit as h approaches 0. And now when we do that, this becomes exactly the slope of the tangent line. So I know that kind of seems like magic. Just hold on for a second. And we'll talk about it. So what happened? H became, we take the limit as h becomes approaches 0, which means essentially it's going to be arbitrarily small. That forces these 2 points, the estimation point and the point of tangency, to become arbitrarily close. They're infinitely close. And that means that the estimate becomes exact. It's no longer an estimate because those 2 points are infinitely close. We get the exact slope of the tangent line. Now, to help you understand that, what I want to do is I want to kind of isolate a small section here, just right around that point of tangency, and take a look at it bigger. So here's the graph in green and the tangent line in yellow. And what happens is our estimation point is coming in closer and closer as h approaches 0. It's coming in closer and closer. You could see here it's still an estimate, here it's still an estimate, here it's still an estimate. It's always still an estimate, but as we get infinitely close, the estimate becomes exact. We're essentially finding the slope at a single point. And that's pretty amazing. Before this limit, we couldn't do that. We had no idea how to find the slope of the tangent line. Now we take this limit, and it's actually, this limit is the definition of the slope of the tangent line. And not only is it the slope of the tangent line, but it's also, this is the derivative. It's the definition of the derivative. So the derivative is just the slope of the tangent line. And that's pretty cool because the derivatives are essentially half of calculus. Okay, I hope this helps, and I'll see you in the next video.